Hi again, guys. I know a few lessons ago I promised that I would talk a little bit more about black bodies and the blackbody spectrum, so here we go. Okay, first of all, what is a black body? A black body is something which absorbs and emits electromagnetic radiation at all frequencies. A good example of a black body is graphite. It absorbs all the frequencies and emits all the frequencies as well. Another quite a good example is planet Earth. So a few lessons ago we were talking about the black body curve or the black body graph. Let's just go over that a little bit. Okay, I'm sure you can remember the graph on the left. We said that if we increase the frequency, we increase the intensity. But we can only increase the intensity so far before the laws of quantum mechanics kick in and the intensity dies down then as we increase frequency. The diagram on the right here also demonstrates exactly the same thing, but instead of using frequency, we're using wavelength. Now remember that wavelength is inversely proportional to frequency, so therefore as we decrease the wavelength we increase the intensity until the laws of quantum mechanics kick in and start decreasing the intensity, as can be seen by the green line here. Now in physics it's possible to draw the graphs in both ways, and let me give you some examples of that. So this graph uses intensity against frequency. These numbers with a K after them, 300, 1000, 4000 and 7000 K, those numbers represent the temperature of the body emitting electromagnetic radiation. So this shows 4 different bodies at different temperatures and shows their black body curves. Also on this graph we can see where infrared, the visible light spectrum, and ultraviolet actually fall on the frequency axis. Okay, let's have a look at another example. Instead of using frequency, using wavelength. So this is a very similar type of graph, but it's the other way around, of course, and we're using wavelength. Notice here we are also showing the visible spectrum, but this time it's on the wavelength axis. And once again these numbers in Kelvin represents temperatures and the different temperatures of the bodies emitting or absorbing electromagnetic radiation. So before we go any further, I just need to speak a little bit about temperature here. This scale here with the different colors represents how hot a body is, or how hot something is. If you were to put a piece of graphite in the oven and heat it up, for example, to 3000 degrees Kelvin, it would start to glow this orange color. If you were to heat it up to 6000 degrees Kelvin, which I think would be a little bit difficult to do in your oven, but if you could heat the piece of graphite up to 6000 degrees Kelvin, and then it would start to glow white. Right? Now if you really heat it up a lot, it will actually start to glow a very, very light blue. If you heat it up any more, it'll start to emit ultraviolet light. At the other end of the spectrum, if you only heat it up to 1000 Kelvin, it glows red, but if you heat it up less than 1000, or quite a lot less than 1000, it doesn't really glow at all, and that's because you can't, well, it is glowing, but you just can't see it glowing. It's not in our visible spectrum, because we cannot see infrared light. Likewise, we cannot see ultraviolet light. Okay, we're at a website called wolfram.com. It's worth checking this website out, actually. If you search for blackbody radiation in the search box, it will come up with some very, very interesting graphs. And if we look at this graph, it shows us some very interesting things about blackbody radiation. Now, on the left here, it shows intensity. Well, actually it's called irradiance, and it's measured in watts per cubic meter, so power per cubic meter. And on the bottom we've actually got wavelength. Now at the top we've got a little scale which we can drag across. Have a look at the temperature here. At the moment the temperature is 1500 degrees Kelvin, and we're going to increase this, and then I'll explain what happens as we increase it. So as we increase, we can see the blue line here is the blackbody radiation curve, which is actually rising up because the intensity is increasing. That's the main point of this graph, is just to show that as we increase the temperature, that's the irradiance, or the power per cubic meter, goes up. Notice here we have the visible spectrum, yes, just here as well. Okay, we're going to have a look at another graph on the Wolfram demonstration site, and here it is. It's a very similar graph, except they've normalized the intensity, so you won't see the intensity increasing, but you will see how the blackbody curve actually shifts and moves as the temperature increases. So at the moment we are at a temperature of 3000 degrees K. Now let's increase that slowly, and as you can see the whole curve is moving. Now let's put it at about 3700 K. If you look here, this shows the color which the object, let's say it's a piece of graphite in your oven or something like this, shows the color at which the graphite will be glowing if you heat it up to 3700 degrees K. And that's because we can only see in this visible light area, and most of the visible light, as you see, is red. Yes, only a small little bit is purple and blue, right? So if we were to take the average of all this color in here, it would be this color. Now let's increase it a little bit more. Let's increase it to the temperature of the sun, which is about, I think it's about 5800, I think. Oh, I've gone a little bit too far there. Let's put it, okay, 5700. Okay, right? So that's nearly the temperature of the sun, and you can see, well, you know, the sun does sort of glow white, doesn't it? There's a little bit of sort of yellow there, but the sun does sort of glow white, right? And if you were to take the average color, yes, if you mix all these colors together, this is the color you would get. Now, as we increase the temperature even further, we start going into the ultraviolet range, yes, which so if you look at the average color now, the average color within the visible light is blue, and let's increase it fully. Okay, so now even though most of the electromagnetic spectrum is in the ultraviolet light, we can't see that, but we can see the visible light, and most of the visible light is at the blue end of the spectrum. So at 10,000 degrees Kelvin, which is rather hot, things glow blue. Okay, I'm going to use this button again to reduce the temperature. Watch the shape of the wave and watch how the average frequency of the wave moves as I reduce the temperature. So now we're getting into sort of the visible light area, and if we stop just actually if we stop about here, maybe a little bit more, if we stop at about 6300 Kelvin, yes, our object would be pretty white at that temperature, and that's because if we take the average of these colors, mix them all together, it would be white. Okay, let's reduce the temperature a little bit more. Okay, so now we're getting a sort of red glow as the object is cooling down. And then now most of the heat is being emitted within the infrared spectrum. We can't actually see infrared light, but what we can see the orange color, which is the average of the visible light. So just by looking at the color or analyzing the spectrum of the black body, we can actually tell the temperature of an object like charcoal. So next lesson we're going to be looking at blackbody spectrum, especially in the infrared area, which is where heat is given off, and we're going to see how this blackbody spectrum helps us to understand how the Earth is absorbing and emitting heat from the sun. So see you next lesson.